begin. So the title's going to be Macromolecules / biological molecules. Jeez Louise. Okay, so macromolecules we're going to look at. Macro means large. Okay, so macro means large. In particular, we're talking about 3 then, macromolecules. 1 are carbs, 1 are proteins, and the other one are lipids. So we are going to aim to do all 3 of these in today's lesson. So we're going to abandon my lesson plan and just do this. Okay, so we'll start then with the first one, which are carbohydrates. Okay? So carbohydrates are a source of energy. That's their main function. However, there are other functions which we will talk about in a second. I thought I could make it bigger, but I can't. Why can't I scroll down?
So have you ever used this app before?
Yes. Ish. Okay, so carbohydrates, for every single macromolecule, you start them as polymers, and then they get broken down into monomers. So we need to know the polymers, and we need to know the monomers. You also should be able to tell me the types of reaction that break down a polymer into a monomer, but conversely build up a monomer into a polymer. So a polymer is broken down. I have said to you recently the word lysis means to break things down. So we just put the word hydro in front of it because hydrolysis is the name of the reaction that breaks down a polymer into a monomer. The easiest way to remember it is that lysis is breaking things down. The opposite then, when I bind monomers together to make a polymer, that is a condensation reaction. Which means you're making water. So in terms of then carbohydrates, you should be able to name the polymer of carbohydrates, and you should be able to name the monomer of carbohydrates. You should also be able to name the dimer of carbohydrates, dimer meaning 2. So the polymer of carbohydrates is a polysaccharide, which quite literally means many sugars. A polysaccharide gets hydrolyzed to a disaccharide, which is 2 sugars, and a disaccharide gets hydrolyzed to a monosaccharide. You should be able to name at least 4 polysaccharides, at least 3 disaccharides, and at least 3 monosaccharides. Do you want me to move on yet?
No, but I was nearly there.
You should have said no. So now I've got me having a little chit chat on our video. To the others. So this title is going to be monosaccharides. Why did you?
I think where's your recording?
Oh yeah, it's going to be a video with my voice in.
Oh, that's so cool.
So when you go back on, you can go ta-da and realise I'm saying ta-da. So this one is monosaccharides. Yeah. So you can set it up however you want. That's why I'm not good enough. I don't know how to do that. Sienna wants it on there. Okay, and now we've named her as Sienna, so it's on there for life. Okay, so we're going to focus on monosaccharides. Obviously, the most important monosaccharide is glucose. The reason glucose is the most important monosaccharide is because in an ideal world, this is year 13 content, but in an ideal world, glucose is the respiratory substrate. What I mean by that is it's the main substance we should use to respire. Should be in the operative word because you can use others. But glucose is the most important monosaccharide. Actually, it's the most important monomer probably in terms of life because it allows us to have that function. So you then should be able to tell me about the two different types of glucose. We have alpha glucose and we have beta glucose. Alpha glucose looks like this. And beta glucose looks like this. Okay? Difference though. In alpha glucose, the hydrogens are always at the top and the OH groups, or the hydroxyl groups, as sometimes they are called, are always at the bottom. In beta glucose, one of the groups, the OH and the H group, is inverted. Which we'll talk about the importance of that in a second. You would be expected to be able to know, describe, and draw the structures of alpha and beta glucose. Okay? So, we're now going to move on to looking at disaccharides. I'll talk about the importance of both of them in a second, but we'll now look at disaccharides. Again, if glucose is the most important monosaccharide, the most important disaccharide is maltose. Because maltose is what happens when glucose combines with glucose. Next one. So my next subtitle is going to be, me shouting you're all wrong, doesn't bode well. So now we're going to look at maltose. Okay? So can you draw, please, and I will do it, two alpha glucose molecules next to each other. I'm trying to work out how to highlight all the red stuff and move it up, but I don't like it. But okay. So I have now got two glucose molecules next to each other. A maltose is when alpha glucose and alpha glucose binds together. It binds together in a condensation reaction. So I want to produce water. So you are looking to take water away from the two molecules. So the OH groups are next to each other. Hopefully in your diagram you've drawn them next to each other better than I have. So those OH are next to each other, so I remove the water because it is a condensation reaction. Which means you are then left with this. All right, So all I've done then is I've removed the water. I still have this H. I still have this H. I removed the water and they are bonded together by this O in the middle. But I've removed the water. This is a glycosidic bond. Glyco meaning sugar. So if we think again about that chemical formula, I've done C6H12O6 plus C6H12O6 goes to C12H22O11 plus H2O. So the chemical formula of maltose is C12H22O11 because we've removed the H2O in the condensation reaction.
Wait, what were the other no monosaccharides?
I'll do that now.
When you're out of space.
Oh, that's a disaccharide.
It's fine. Just do another one. So, we've just done maltose as one disaccharide. Maltose is made up of glucose plus glucose. Okay? There are two other then disaccharides you need to be aware of. One is sucrose. Sucrose is very important, particularly as sucrose is what most of us have as the sugar in our tea. It is the sugar that is largely produced as the storage sugar in plants. So last year in GCSE, when you did about translocation, which is the movement of sugar in a plant, we're actually talking about the movement of sucrose. This year, when we do translocation in more detail, we are going to be talking about the movement of sucrose. So sucrose is the main sugar that is transported in plants as a result of photosynthesis. So sucrose is made of glucose, and the sweetest of all the sugars, which is why it's found in fruit, fructose. The final disaccharide that you need to be aware of is lactose, which is the sugar found in milk. And some people are intolerant to it. Do you want to include that in the video? Including Lily Jefford. So, lactose is made up also of glucose. So you can see they're all made up of at least one glucose. And the other monosaccharide, galactose. No. The reason people are intolerant to lactose is because they do not have the enzyme lactase. As we all get older, our production of lactase wavers. So my daughter produced a lot of lactase because she needs it to break down lactose. As we get older, adults shouldn't need milk, so our production of lactase reduces. Some people it reduces too quickly, so they become intolerant. Let's rock and roll. So, polysaccharides. Literally meaning many sugars. The foundation and backbone of life is built around polysaccharides. So no living thing will exist without the existence of polysaccharides. So these are all incredibly important. And we should be able to name several polysaccharides. In fact, we should be able to name 1, 2, 3, 4, 5. Okay? So let's see how we get on with 5. So the first we're going to do is the polymer of alpha glucose. Right, this can get fiddly. Okay? That was jazzy. Come on, give it to me.
Did you not do that last time? You just did it.
No, I just drew them. I've now just copied it so they're all identical.
Yeah, but you tried to copy it last.
Yeah, and failed. But always learning, yeah? Okay, so I've now started to build a polymer or a polysaccharide. So we've got our glycosidic bonds here. Right, so we're starting to build a polymer. We've got these alpha glucose molecules all bound together in a condensation reaction. We've got our glycosidic bond in between our monomers. All right? Okay, I'm now going to add more complex detail to it. Can I zoom? Yes, I ruddy can. Okay. Remember earlier when I was counting on the board, the carbons. Carbon, 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 carbon. Okay? Glucose C6, so I've got 6 carbons. It's a hexose sugar. Right. This bit's now important. In the first polysaccharides, the bond we form are in between carbon 1 and carbon 4. So the carbon 1 of one monosaccharide is binding next to the carbon 4 of another polysaccharide, of another monosaccharide. So we form, so this bond here, to give it its more accurate name, is a 1,4 glycosidic bond. Say again? However, what can also happen though, is I can also have a bond that forms here by my carbon 6. So I can also form what's called a 1,6 glycosidic bond. Which means eventually I end up with a polymer of alpha glucose looking like this. So you've got your straight line there. I have a straight linear line of 1,4 glycosidic bonds. Yeah? Make sense? That's just where they'd all just bond in a straight line. That then, if I just have all 1,4 glycosidic bonds, that creates a very good store of glucose. So imagine going to like the Amazon storage facility where they have all of the packages all stored up in one massive long aisle of one thing. So imagine you're going into Amazon trying to order a That's Not My Giraffe book. Wonderful book, exceptional read. I actually read That's Not My Elephant this morning to Isla. She really enjoyed it. Anyway, we digress. So imagine you've got all of the That's Not My books in one aisle. Here I have my store of them all in one line. It's a very good store. This storage molecule is, of course, starch. Because starch is a store of glucose. But as we move into A level, which is what we're doing now, the straight linear chain of 1,4 glycosidic bonds has got a particular name called amylose. And you might now be able to remember back in your GCSE biology names that the name of the enzyme that breaks down starch is called amylase. It's because amylase breaks down amylose. Yeah?
Yeah.
Wonderful. Let's move on. Oh no. That's clever, isn't it? Wow. Okay, so that's if I have a straight linear chain, that's amylose of 1,4 bonds. However, what can happen then, as well as we having my 1,4 bonds, we then can start to get branches coming off it. So this one contains 1,4 and 1,6 glycosidic bonds, which creates a branch. Which means, so rather than Amazon just having one massive aisle, which could go on for miles, if I add more aisles to my Amazon storage facility, I can store more things. So this branched molecule is actually even better at storing things. So this is also an example of starch. But rather than it being amylose, because it's branched, it's called a myelopectin. So in plants, glucose is stored as amylose and a myelopectin. Myelopectin is more branched, which means you can store more. They are called branches. The reason why it's better to be branch is if you think about this here. If I wanted to hydrolyze starch, if I only had amylose, I could only gain 2 glucose molecules every time I break it down, because you can only do it from the terminal ends. Whereas if I had a myelopectin, just even in my example on the board, I can do 1, 2, 3, 4, 5, 6, 7. So it releases glucose far more quickly. So we've done starch. So just as a little reminder, starch is a glucose store in plants. We are not plants. Okay? So we do not store glucose as starch. We store glucose, and all animals store glucose as glycogen. Fundamentally, they are the same things. So glycogen is a glucose store in animals. And the same then as amylose and a myelopectin, the basics of any polysaccharide are a 1,4 chain of glycosidic bonds. But glycogen also contains branches, but as young Elliot Ferguson, fastest 200-metre runner in the world, YouTube sensation. This one has got even more branches than a myelopectin. So it's a heavily branched chain, which again means it's even better at storing glucose. So this is glycogen, so it contains 1,4 and 1,6.
All the other little branches ones.
So if it goes up, it's 1,6. If it goes across, it's 1,4.
Okay, but the branches can go either way.
They can. So it is heavily branched, which means it can release large quantities of glucose. So if we go back to what I did earlier, if I had one round of hydrolysis, in starch or amylose, I could only release 2 in my diagram. In my diagram of a myelopectin, I release 7. If I just do a very quick comparison to this one, I will release 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33.
You missed one. Like that.
34. Okay? So all these structures are very similar, but you can clearly see that having more branches means that in one round of hydrolysis, this will release far more glucose and amylose, which is just a linear chain. Okay, so we now have here cellulose. I have here then 2 glucose molecules next to each other. Again, let's add the key bits. H, OH, but remember, because these are beta glucose, the H and the OHs are inverted. All right, so now we have an issue, because when we bound 2 alpha glucose molecules together, we want to bond an OH with an OH. The reason we bond, as a reminder, the reason we bond an OH and OH together in a condensation reaction is so we can release water and be left with the oxygen, which is the foundation of a glycosidic bond. So if beta glucose were to line up like that, it would not work. So what happens with beta glucose is this. I have one that remains like that. Okay? But then what happens is the second one is inverted. So you can now see what I've done is, because one of the other one is upside down, to put it in more simple terms, I've now created an OH next to each other, which now means I can create my glycosidic bond here. So that's how 2 beta glucose molecules join together. That at the moment doesn't look like it's important. But now let me circle why that is important. Because whereas when we had alpha glucose molecules together, all of the lines were pointing up at the same time. Now, I have one line pointing up, so my 6 carbon, that one's going upwards. But in this one here, it's going down. So what then happens is this. You then end up with a structure that effectively looks like this, where the 6 carbon, so if these are my carbon 6, are going up and down, up and down, up and down. So what that means then is this. If I ended up having 2, I know what you're thinking, guys. Yes, I'm IT techie. If I end up having 2 chains, what can then happen, because I've got my CH2OH group, the 2 chains can now bond together. I could have 3 chains, which means 3 chains bond together. I could have 4 chains, 5 chains, 6 chains. I end up creating a chain of molecules like this. Which means it's very, very strong. It's like having a wall, but rather than having one layer to my wall, I'm now adding layers and layers and layers and layers and layers and layers and layers. And you should all be able to recall, we start at the top of the page by talking about cellulose. Cellulose is what makes up plant cell walls. The reason plant cell walls are so strong is exactly because of this. It's because the cellulose chains bond together. We form something called a microfibril. And microfibrils have incredibly high tensile strength.